All right, folks, let's try another example of a related rates problem. This one also includes a right triangle. I call this the airplane problem, but it doesn't have to be an airplane. I've seen this problem done with a baseball where somebody's running from second base to third base. But in every situation, it's always a right triangle. The thing that's interesting about this right triangle problem compared to the last two we did is in the latter problem, the two legs were changing and the hypotenuse was constant. In the car chase or the car crash problem, both legs were changing and the hypotenuse was changing, so everything was changing. This is the only third possibility that you can have. The third possibility is when one leg is constant and the other leg is changing and the hypotenuse is changing. Okay, so anytime you have a situation where the hypotenuse is changing and one of the legs is changing, but the other leg is held constant, I call that the airplane problem, but you can call it something else if you want to. So let's look at this. It says an airplane is flying north. So that direction right there, that's north over there. Oops, that's an M, that's not an N. Sorry about that. That direction is north, okay? So this direction is south. An airplane is flying north at an altitude of 5,000 feet. 5,000 feet. So that means that the altitude of the airplane is not changing. It's flying steady at 5,000 feet with a speed of 290 feet per second. That's the rate of change. The plane is about to be directly over a building that is 12,000 feet south of a septic tank. Okay? At the instant when the airplane is over the building, at what rate will the distance between the airplane and the septic tank be changing? So let's call this C. That's a hypotenuse, the distance between the airplane and the septic tank. And now you may be thinking, wait a minute, if that building is 12,000 feet south of the tank, then isn't this a constant? Isn't this not changing? The height is 5,000. Does that mean the 12,000 is also not changing? No, this is changing. It's just that we're saying that the airplane is the horizontal distance between where the airplane meets the ground, directly underneath the airplane. That distance to the tank is 12,000 feet. But as the airplane continues to fly this direction, then that height, or excuse me, not that height, that distance is going to get shorter and shorter and shorter. So the horizontal distance, not the diagonal distance, this is the diagonal distance, but the horizontal distance along the ground between the plane and the tank is getting shorter. So we're going to call this A, and we're going to call this horizontal distance B. And so what we could do actually is we could change this. Watch this. What we could do is we have this triangle here, but we actually could create another right triangle, and this is really the one we're dealing with, where it goes out from the plane and then comes down and creates a right angle. And now hopefully you can get a better understanding that this distance is getting shorter because the airplane is flying that way. Okay? So we're going to call this height A, which is still 5,000 feet, because if the plane is flying at 5,000 feet, it'll be at 5,000 feet the whole way. So A is 5,000. But this distance, the other leg, B, that's changing. The airplane is flying. And how fast is the plane flying? The plane is flying at 290 feet per second. So this distance here is getting smaller at the rate of 290 feet per second. Okay? So let's go ahead and go through our steps here. Identify the given rates. Well, we're only given one rate in this problem, 290 feet per second, and that's the speed of the airplane. The speed at which the airplane is flying north is 290 feet per second. And that's side B, or leg B, so we're going to say dB dt is, now we're not going to put 290 because what's happening to this leg of the triangle? It's getting shorter. So that's going to be negative 290. Okay? Identify the unknown rate. All right, step 2. The rate we want to know is the rate at which the airplane is getting closer to the tank by a straight line. And that is the hypotenuse. That's c. So we're trying to find dc dt. We don't know that, but we're going to find it. Step 3. Identify a formula that relates these variables. Well, this is a right triangle, and we're dealing in the length of A, the length of B, and the length of C. Again, Pythagorean theorem. So we're going to put A squared plus B squared equals C squared. Okay? Step 4, plug in for constants. Are any of these variables not changing? Well, A, the height at which the airplane is flying is 5,000 feet. It's staying at 5,000 feet. And so we're going to plug 5,000 in for A. 5,000 squared plus B squared is equal to C squared. Okay? And then step 5 says we're going to ddt every term. So step 5, we want to do the derivative. Well, the derivative of 5,000 squared is 0. So that's going to cancel. And now we only want these two. The derivative of b squared is 2b db dt is equal to the derivative of c squared is 2c dc dt. So we have 1, 2, 3, 4 variables. They gave us db dt, so we'll plug that in. And then the question says, let's see, at the instant when the airplane is directly over the building, that's when the airplane is 12,000 feet. That's when the airplane is 12,000 feet south of the tank. And so that means the distance from here to here is 12,000. So B is 12,000. Okay, so here, step 6, we'll plug in 2 times 12,000 for B. dB dt is negative 290. And it doesn't matter that we're using these big numbers. Well, I don't call them big, but you might call them big. There are no big numbers. Not in math. There's no big numbers. And then we have 2 times c. Now we need to solve for c. We need to use the Pythagorean theorem here. So we have 5,000 squared plus 12,000 squared equals c squared. Okay? Now they're going to use up a lot of space in our calculator, but we're going to go ahead and do it. What I'm actually going to key in is if I were to take the square root of both sides, I would get c is equal to the square root of 5,000 squared plus 12,000 squared. So that's actually what I'm going to key into the calculator. I'm going to key in the square root of 5,000 squared plus 12,000 squared, and I get 13,000. So I'm going to put 13,000 in for C, and then dc dt. dc dt. Okay? Now I'm just going to do a bunch of algebra, arithmetic, calculations, and solve for dc dt. So 2 times 12,000 times negative 290. Okay, well that's negative 6,960,000. Okay, equals 2 times 13,000 is 26,000. dc dt. And now all I have to do is divide this number by 26,000 on both sides. Cancel. 26,000. And I get negative, here's what I'm going to write, dc dt. Now I could write this as a fraction, but I'm not going to write it as a fraction. I'm going to put it in as the decimal here. Negative 267 point, I'm going to go 4 decimal places. 6923. We're dealing in feet. How frequently? What's our time variable? Feet per second. And so the rate at which the airplane itself is getting closer to the tank on a diagonal is it's getting closer at 267.6923 feet per second. Remember, all the negative means here is that it's getting closer. We wouldn't actually interpret the negative needs to be interpreted in language, not written as a number. The negative means it's getting closer, so we would just say that the airplane is getting closer to the tank at the rate of 267.6923 feet per second, okay? And that's the airplane problem.